All right, Mr. Arnold here. We've got Alex, we got Carson. Going to go over Waves Unit 7 review. Carson's already put a Quizlet up there for me, so we have a little bit of vocabulary review for you if you want to work on that. If not, you can just listen to this. I don't know what else is going on. Waves. There are a couple things we need to know about waves. First and foremost, there are two different types. Type number 1, type number 2. The first example, number 1 up here, is showing us a transverse wave, and that is because the particles are moving at right angles. So the particles are moving up and down here, but the wave is actually moving to the right. So when we have waves where particles are moving at right angles to each other, that's a transverse wave. The bottom wave, wave number 2, is actually a either longitudinal or compressional wave. Again, science is always great. We have two names for the same exact thing. Don't know why, but it does make sense here. And this one, the one that I think of the most, is a slinky, where it squeezes together and then it stretches out. And so you have the little bit of the squeeze and then it stretches. A little bit of a squeeze, then it stretches. The particles are all vibrating in the same direction as the actual wave itself. So first of all, those are our two types. If you're at a Reds game or a Bengals game and you're doing the wave, you're doing a transverse wave. If you're stuck in a crowded hallway where you're bumping into each other back and forth, you're more like a compressional or longitudinal wave. Good so far? All right. So that being said, we do have some different parts that we need to be aware of. We've got A, B, and C, and actually D up here. So if we're looking at A right here, A is representing what part of our wave? It is not the pizza crust. It is simply the crest of the wave, which is the highest point on any wave. If we're taking a look at B, we're not at the highest point now. We're at the lowest point. That's a trough. One way you can remember when you feed pigs and cows and stuff, you typically put it in a trough, which is a big U-shaped bowl where they can go and eat from there. So we have the crest, which is A. We have the trough, which is B. And then we have C here, which is the height between the crest and the trough, the height between the crest and the resting position, or the resting position and the trough itself. And that is the amplitude. Amplitude really relates to energy. The higher the amplitude, typically speaking, the more energy we actually have. And that's assuming that all waves are the same wavelength. And we got to talk about that a little bit later on. Last thing that we have for transverse waves is the distance between two crests is going to be our wavelength, and that's some form of meter, whether that's nanometers or whether that's kilometers. It just depends on what we're talking about. It could also be the distance between, if we had another trough out here, it could also be between trough to trough. Good so far?
Yes, sir.
All right, so now let's take a look at our compressional wave. All the parts are kind of comparable to each other. We can measure the same things. We still have wavelength. We still have amplitude. We still kind of have a crest and trough. We just call it a different name. So we have A here. A is where all the particles are squeezed tightly together. That is called the compression. All right. It's very much similar to A up here, which would be the crest of a transverse wave. Now we have B here, which is a big section where all the particles are pushed out or stretched out, and that is the rarefaction. And the rarefaction is kind of like the trough, the opposite end of a transverse wave there. Again, we have another compression, another rarefaction, another compression right there. So we can measure wavelengths similar ways. We can measure from compression to compression, or we could measure from rarefaction to rarefaction, and those should be equal. And we can also measure amplitude. Amplitude is going to be how tightly those things are compressed together. The more tightly it's compressed together, the more amplitude that compressional longitudinal wave has. Questions about waves?
How do you calculate?
How do you calculate? In a transverse wave, it is simply measuring it with a meter stick, ruler, or whatnot from there. Same thing kind of with the compressional wave, but you're going to have to use some computer generations to see exactly where all the compressions are coming together. Don't worry about the the compressional one. I won't ask you to do that. You'll just need to be able to use a meter stick or a ruler for the transverse one. Pretty easy. All right, so we're going to move on to, and I got to move my fan over here, over to the next slide here. Talking a little bit about frequency. What is the frequency of a wave? How many crests, or we could substitute in troughs. Doesn't matter. We could substitute in rarefactions here, or we could substitute in compressions here. Pass a point per second. And sometimes you have a big lazy wave, where if this is the starting point over here, you don't have a lot of crest passing, so it's not a very frequent wave. Or you could have a real wave like that where you have a ton of crest and now you have high frequency. What do you notice about the wavelengths and frequency?
The one that has longer wavelengths usually has a lower frequency.
Yep. Typically, again, if amplitude and stuff are all the same here, the one that has the longer wavelength has lower frequency. The one that has a shorter wavelength typically has higher frequency. And again, we are assuming some things here about amplitude and stuff, which we will find out a little bit later on about. So we've covered frequency, we've covered wavelengths, we've covered amplitude, we've covered the different parts. Pretty good so far? Makes sense? Makes sense? Good. So both of those guys think it makes sense. All right. So how do we calculate wave speed? It's simply a function of wavelength, which this upside down looking little y kind of thing is called lambda, the Greek letter lambda, which represents wavelength, times the frequency. So how fast is it going past that point? What is the wavelength of that wave? Will tell us how fast that actual wave is moving in some form of meters per second. It could be nanometers per second or, you know, kilometers per second, depending on what type of wave we're actually attacking.
Write down the formula.
You will need to know the formula for the test. You will have some. No, as long as you know the formula and you know the right units, which it's meters for wavelength, it's hertz for frequency, and then meters per second for wave speed. Sure. Yes, you're going to need to know the wavelength and the frequency. So if you go back to the kind of the beginning of the year, we kind of had that cheater triangle that we were using to set up to kind of remind us of what it is we're doing. So if we're trying to solve for wave speed, it's simply wavelength times frequency. So we can do wavelength times, it's not, there it goes, times frequency. And again, we can cover up anything that we need. If I want to try to find frequency, if I cover up, hang on a second here. If I kind of cover up my frequency, it's going to be wave speed divided by the wavelength, and vice versa is the same from there. I believe there's an undo button somewhere over here or a back button. I don't know.
Right here.
Carson's going to help me. Go ahead and hit it, Carson. Don't screw it up. One more.
Ta-da.
All right, so Carson didn't screw everything up. So we can use this triangle to kind of calculate, but you're going to get word problems like, you know, Alex is measuring a wave that has a wavelength of 10 kilometers and has a frequency of 2 hertz. What is the wave speed of that? 10 times 2 is?
Oh, sorry. 10 times 2 is 20.
10 times 2 is 20, so the wave speed would be 20 kilometers per second. Okay? So that's just wave speed. It's pretty simple. I'm not gonna. There's only a handful of questions, and I know for a fact there are practice worksheets that you can use on the unit guide as well. Wave behaviors. How do waves interact? How do they behave with each other? There is 3 different types that you need to know: reflection, refraction, and diffraction. Basically, all talks about how waves are hitting or striking surfaces and how do they react. Reflection is one that you guys all pretty much kind of would get. It's when it bounces off of something. So if I look into a mirror at a certain angle, it will hit that mirror and it'll bounce off at the exact same angle, and that's called reflection. All right? Have you ever made an echo?
Echo.
What an echo is nothing more then reflection. Yep, so the sound waves bounce off of a wall, a cave, or in an empty hallway, and they travel back to you, and you hear that. So reflection is where it just simply bounces off and returns or travels in that same angle.
It comes back to the same resolution, right?
Typically, depending on what angle you actually have. So refraction is not bouncing, it's bending, all right? And that's because we're going through two different mediums. So we're going from air to water, or a solid to a liquid, something like that. We're transferring from one type of medium to another. The one that most commonly is used is if you are trying to look at, and I have a horrible drawing, little fishy swimming around. We're going to draw Mr. Arnold here. Yay. Mr. Arnold is trying to see the little fish, all right? And when Mr. Arnold's light waves from his eyes travel down, we assume that it is traveling straight at the fish. But in reality, what happens is when we cross from the air to the water, it gets bent a little bit. So in fact, what Mr. Arnold is seeing is here, and it gets bent down, so the fish is not exactly where I think it is. If you've ever seen any of the videos of people trying to spear a fish, you always have to aim at a different spot. Typically you aim a little bit in front of it, because those light waves are refracted, and they get bent as they pass. If you are that kind of person and you are running and jumping into the pool and you're trying to land on your buddy, you have to jump and aim at a little different spot because your buddy's not exactly where your eyes think. You guys have all seen a cup of water with a pencil in it and the pencil looks like it's broken. That's a perfect example of refraction. We pass from air to glass to water, and that's what creates that, making it want to look like it's broke.
Do you need on the assessment to draw?
You do not need to draw a picture, you just need to know what they're doing. Diffraction is kind of like refraction. It is the bending, but it's bending around obstacles. So this happens a lot in waves, especially if you've been to the beach. You have these lovely, lovely water waves. These water waves are coming in, and let's say we have a pier or some sort of block. As those water waves hit, they will eventually, and again, they'll kind of keep their form, and eventually they will start to reform right around the other end. This is how you can hear somebody running down the hallway even though you don't see the person. Maybe they're around the corner, because sound waves will bend around corners and things like that and then meet back up. If you've been to hospitals, up in the upper corner on any of the corners, what do they typically put? Like if you're walking in the hallways of a hospital, in the corners, as you're getting ready to turn around corners, they typically have mirrors so that you can see what's coming, because they can bend around those corners and stuff like that. So, yep. So we have diffraction, which is bending around an object. We have refraction, which is bending as we pass from a different medium to another medium, solid to liquid, liquid to gas. And then we have reflection, which is all about bouncing off of that surface. Good?
Yep.
Almost done, I promise you. Promise you. What happens when waves actually interact? Well, there's two things that can happen. It is either constructive or destructive, and the names imply exactly what we're talking about, right? Constructive, if we're constructing something, we're building something up. It adds to the amplitude. Good. So here we have the blue wave and the red wave. They both hit at the same time. We have both crests lined up. Let me change colors here. Both of the crests are lined up, the troughs are lined up. Because they're lined up, they're in unison or sync with each other, you're going to end up with a wave that has a bigger amplitude and a bigger trough, and it makes it double the size of that it originally was, or triple depending on how they're adding up. Over here, we have destructive. The crest of one wave is matching up with the trough of another. They're canceling each other out. So the resulting wave is a smaller crest, smaller trough, or it could be no wave at all, if the wavelengths are the same size. Noise canceling headphones, if you wear those, what they do is they emit sound waves that match the sound waves of the music, or the surrounding area, so that you don't hear any of that, just the music that you're listening to. In fact, if you could do it, if you stood in a square room, put speakers in each one of the corners, turned them on, you could stand in the middle and you wouldn't hear anything, because the sound waves would cancel each other out right in the middle, if it was the same wavelength, wave frequency, etc. from there. So that's constructive, destructive. The last part, you don't need to know a ton, you just need to know the order and what's happening with the frequencies. So we have the electromagnetic spectrum. We talked a little bit about that with Doppler effect, red shifting, blue shifting, same kind of ideas going on. You have radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, gamma rays. That's the order from longest wavelengths to the shortest wavelengths that we know of. So if we're over here with the long wavelengths, we have low frequency, but we also have low energy. Over here with gamma, these guys have the smallest wavelengths, which means they have the highest frequency, they have the most energy. These are the ones that can cause a lot of damage. All right? Cancer and stuff like that is caused by these waves, because the energy they have can actually alter your genetic information. All right? So if you watch the Incredible Hulk and stuff, I believe that was all about gamma rays and stuff like that, and then it turns green, gets real big, and beats the crap out of people. Woohoo! Nope, not like me. So other than that, the only other part that you need to know is the visible part of our spectrum, which is about 400 nanometers to 700 nanometers, and that is the whole rainbow, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. As we move from Roy to violet, Biv, whatever, the actual wavelengths decrease. So we're getting smaller and smaller as we move towards the violet end of our spectrum. The energy would be increasing if we're decreasing those wavelengths, yes. So you could think of it as violet light has more energy than red light has, all right? So you just need to know that order. 400 to 700 nanometers is all our eyes are able to pick up on. If it is longer than 700 nanometers, we won't be able to detect that. That's infrared and microwaves and things like that. If it's shorter than 400, we're not able to pick that up. That's ultraviolet light, sunlight, X-rays, which we can't see. So our eyes are only tuned into certain wavelengths that we can physically pick up on. People who have like red-green colorblind, or they have some other issues with their eyes, is because their eyes are not able to pick up on very specific wavelengths. And those wavelengths then are perceived by our eye, transmitted as an electrical signal to our brain, and that's why green is green, red is red, and blue is blue. So, questions? Good? Questions? I did not bring lunch. I'm a little upset about that right now. All right, well, if that's all we got, if you ever, you got units, this is Unit 7, got to make sure that we get this done here shortly, wrapped up, and move on to Unit 8. As always, if you got a question, come get me.